So we've talked about two of the consequences of the second law of thermodynamics. And those two consequences were that heat flows from hot to cold, and heat engines and pumps have a maximum efficiency, and that maximum efficiency is lower than what the first law says. Again, the first law says, oh, you can be 100% efficient if you can reduce your exhaust to zero, and the second law says you have to have some exhaust. So I want to talk about why. Why do these things happen? What's the real second law of thermodynamics? Because these two are just results of that second law. Okay, so let's draw two systems. Two systems that sit next to each other. That's a little more than. That's okay. Okay, so I'm going to start these guys. Two systems of gases, and the left system has molecules that are moving on average faster, and the right system has molecules that are moving on average slower. All right, so if you let these two systems interact for a while, sometime later, you're going to find that the system on the left is going to have molecules that are on average moving slower, and the system on the right will have on average molecules that are moving faster. All right. In other words, heat has moved from the hot system to the cold system. And you can model this statistically. You can say, okay, how likely is it for heat to go one way than the other? So the arrow this way, this is likely to happen. But the arrow this way is unlikely. Okay, this is really just a retelling of what we've already said, right? But we're kind of just imposing it. We're not really explaining it. So let's draw another system. Let's just draw a single system now. And there. Okay. So here's our single system, but let's make this a very specific system where the molecules are very ordered. All right, so let's say this is a box of gas where I put all of the nitrogen molecules in specific spots, right? And if I let this system evolve over some time, those molecules are going to be in different spots. Trying to make sure I made the same number of spots. There. The box on the left is ordered. The box on the right is disordered. And this motion from order to disorder is likely to happen. Whereas the motion this direction is unlikely to happen spontaneously. All right. So this is one way of saying the second law of thermodynamics, is that systems move from order to disorder. And you can argue that statistically. You can just say, how likely is it that this system is going to go back, after being disordered, that it's going to go back to all of the molecules being exactly where they started? And the answer is, it's just not very likely. It's not impossible, but it's so unlikely as to not happen once in the history of the universe. Right? And so we can say it's just not going to go backwards. All right? Whereas if we have another system, so we could say let this system evolve further, at some point it'll reach a level of disorder where motion from one disordered state to the other disordered state is equally likely. So now it's maximized some measure of disorder, right? So we call this measure of disorder entropy. And again, entropy has a statistical definition, but I don't want to get into that. We'll just say, for our purposes, entropy is a measure of disorder. So the system here has low entropy, and these systems have high entropy. In any spontaneous process, entropy is at best maintained, but probably increased. All right, so any spontaneous process, entropy is likely to increase. It will not decrease. It's just statistically unlikely to happen. Okay, so let me give you one more definition. You can calculate entropy, or at least change in entropy, as heat transferred divided by the temperature at which it's transferred. All right, we're not going to do a whole lot of math with this. I just wanted to give you this because this is going to help us understand why there's a maximum efficiency that's smaller than what the first law of thermodynamics dictates. Okay, so let's draw our heat engine one more time. And let me tell you that we've talked about state variables. State variables are things like pressure and temperature and number of molecules. Entropy is also a state variable. Entropy is a state variable, and that means in a cyclic process, I need the system to come back to the original entropy. I need the system to come back to the original entropy. It means delta S for the entire system, the entire cycle, needs to be 0. So if I draw these things, I say, okay, here's Q cold, and here's Q hot, right? If only, let's write it the other way. Let's do a heat engine. There. Here's Q cold, Q hot, and here's Q cold. And then I get some work out of this system. If the only thing that happens here is work out and Q cold, if Q cold is 0, then I have a change in entropy up here of Q hot divided by T hot, and work out doesn't change entropy. Sorry, let's actually just say 0. Work doesn't change entropy because entropy only changes when heat is transferred. All right. So when the gas does work, it doesn't change entropy. So if this is the case, the system has gained some entropy, right? It's gained Q hot over T hot, whatever amount of entropy that is. And so it's not back to its original state, right? So it needs to dump some entropy, and that's where Q cold comes in. We can dump some entropy by, we'll see, delta S here. So this could be delta S hot, and this could be delta S cold. It's going to be Q cold divided by T cold. So Q cold is smaller than Q hot, but T cold is also smaller than T hot, right? So if T cold is small, that makes delta S bigger, right, for a fixed Q cold. So even though Q cold is smaller, T cold gets smaller to compensate, so that delta S hot equals delta S cold. right? So we can even put those together. We could say, all right, then Q hot over T hot equals Q cold over T cold. And I could also write this as Q hot minus the work put out of the system divided by T hot or T cold. Okay. And you remember efficiency for a heat engine is Q hot over work. So I could solve the system for Q hot over work. So how would I do that? Well, let's cross multiply maybe. Actually, let's just multiply by T cold. So I could go T cold over T hot times Q hot equals Q hot minus the work put out. Okay, and I could divide by the work put out. So if I divide that over, do that, and erase this. Okay. And I can split that, right? Fractions work that way, so I can say Q hot here minus Q hot here. I feel like I did something wrong. Call me out if you think I did something wrong here. Oh, here it is. I got it. That definition's wrong. This is work out divided by Q cold, Q hot. Okay, all right. So this bit is 1. So then I could add this over and subtract this over. And what I get is work out divided by Q hot equals 1 minus T cold over T hot. That's exactly what we said it had to be. Right? And that's the efficiency maximum. Okay. So that's, and you can do the same kind of argument for a heat pump. I'm not going to do that here. So entropy is the reason that heat moves naturally from hot to cold. That's a statistical argument. And in any process, entropy has to be increased. And for a cyclic process, the entropy of the system has to stay the same. All right. And so you can say if you wanted the entropy of a system to decrease. So let's do an example. So what is the entropy of 10 grams of steam, or the entropy change for 10 grams of steam at 100 C when it condenses to water at the same temperature? Okay, so we're taking water, right? Steam. How do you draw steam? Perfect. And condensing it to liquid water. All right, 50 grams at 100 degrees Celsius to 50 grams at 100 degrees Celsius. We're just changing from steam to liquid, right? So what's the heat transfer there? Well, Q equals mLV, right? And it's heat taken away, so that's minus mLV. Okay, so we can do that math. That's not terribly hard. It's 50 grams, which is 0.05 kilograms, times the heat of vaporization, which is 22.6 times 10 to the 5 joules per kilogram. And if you do that math, you get 113,000 joules. And it's negative, meaning we had to take that energy away. Right? So what was the entropy change for that system? Well, it's Q over T. So that's going to be minus 113,000 joules divided by a temperature, and that needs to be the absolute temperature, so it's got to be in Kelvin. So that's 100 degrees Celsius plus 273 to make it Kelvin. If you do that math, you get minus 300-ish joules per Kelvin. So clearly the unit for entropy is joules per Kelvin. And it's negative, right? The system lost entropy. How do I know? Well, because liquid water is is more ordered than steam, than gaseous water. And if I kept taking away energy, eventually I would change it into solid water, which is ice, and that has less entropy as well. So how are we changing the entropy of the system? Well, I have to take some heat away from it. So if I have a closed system, right, if I can't dump heat into it or take heat away, the total entropy of this system can only get bigger. It'll maximize, right, to a certain point. Although if you take, like you say, I put an ice cube and some warm water in a thermos and seal it. The entropy actually does increase. The entropy when they're different temperatures increases until they're the same temperature, but once they're the same temperature, the entropy doesn't increase anymore, and there's no more driving force. And this is the idea behind the heat death of the universe. The entropy of the universe. The universe is a closed system, right? We can't dump heat off anywhere else because there is nowhere else. The universe is the universe, and we can't take heat in from anywhere else. So eventually, everything in the universe is going to come to the same temperature, and we're going to maximize our entropy, and we'll be very boring. And that'll be the heat death of the universe. So you have the second law of thermodynamics to thank for the heat death of the universe. However, our actual deaths will probably happen before the heat death of the universe. That's a long, long time away. So now you know more about physics than you did.